So in this example, we'll be looking at a membrane reactor where we have two different possible reactions that can be occurring. The first of which is A plus B goes to C plus D with this known desired reaction rate over here on the right. And then the second reaction is D plus A goes to E, which is the undesired reaction, and its reaction rate law is over here on the right as well. And so D is our desired product, and we're trying to select for this first reaction and minimize the amount of second reaction that's happening. So that's part of the motivation for using a membrane reactor. And then down here at the bottom are all the givens that we know, the length and diameter of our reactor, the volumetric flow rate, the initial concentrations of A and B, and then the reaction constants for the desired and undesired reactions. So with this membrane reactor, we're going to have the center core and then the outer shell. And this inner part is going to be porous on both sides. And we're going to be feeding in pure B into the center and then pure A into the shell on either side. And so by doing this, we're having A diffuse in along the length of the reactor. And so we're keeping the concentration of A as low as possible down the length of the reactor to try to minimize the amount of the second reaction that's occurring. And so from this information, we're going to first try to calculate the instantaneous selectivity of the desired product versus the undesired product, and then the yield of the desired product as well as the undesired product. So for our first step, we're going to start to write some mole balance equations for each of our species. And so for A, for the membrane reactor, we can write like a PFR. DFA dV is going to be equal to the reaction rate of A, and then we're also going to be adding in A along the length of our reactor, and this large RA is how we're going to incorporate that into the mole balance. And then for B, we have DFB dV is equal to RB. C is going to be DFC dV is equal to RC. And then something very similar for both the product D and the product E. So these will be our differential equations that we're going to put into POLYMATH to help us solve this problem. And so now, second, we need to start to define our reaction rate law expressions. So for the rate of disappearance of A, it's going to be consumed in both the desired reaction, and this was its rate law expression, but then it's also going to be consumed by our undesired reaction that was dependent on the concentration of A and D. And then our reactant B is just going to be consumed by the first desired reaction, and then C will be the product of our desired reaction, and then D will be produced by the desired reaction but consumed by the undesired reaction, and then E will be formed by just the undesired reaction. So now we can plug in these rate law expressions into POLYMATH as well as explicit equations to define what the rate expressions will be in the mole balances that we had just previously derived. So now our third step is going to be to describe the transport of A into the reactor. So this was the RA term that we added to the mole balance of A, and we were going to have uniform diffusion of A in. So for this case, then RA is going to be equal to the initial molar flow rate of A over the total volume of our membrane reactor. So we can split this up into the initial concentration of A that we know that we had and the initial volumetric flow rate that we know that we had, divide that by the cross-sectional area times the length of our reactor, which we can calculate. So Ca naught, nu naught, and then we can plug in for the cross-sectional area, having the diameter of our reactor over 2 squared times pi for our cross-sectional area, and then times the length. And then we're going to have to throw in, since these were in meters and the volumetric flow rate was in liters, we're going to throw in this conversion from meters cubed to liters down here. So now we have an expression for the diffusion of A in through the membrane sides of our reactor. And so fourth, we can look at the reaction stoichiometry. And so here we need to start to define what the concentrations were that were in our rate law expressions, so Ca, Cb, and etc. So for our gas phase reaction, we can express these as the total initial concentration of our reactor times the molar flow rate of A over the total molar flow rate, so essentially the mole fraction of A times the total concentration. And so then we can do something similar for the rest of the species. Okay, so I just finished writing in the expressions for the rest of the concentrations, and as you can see, they're fairly similar. And here we can express the total molar flow rate as just the sum of all the molar flow rates of each of the different components, products and reactants. And then here, Ct naught will just be Cb naught because we were just flowing B in through the core of the reactor, so that was what we had initially started with inside the reactor where the reaction is occurring. So now our fifth step is going to be to add all of the extra equations that we need. So like for the instantaneous selectivity and yields that we want to plot. So the instantaneous selectivity of D as compared to E will be the rate of appearance of D over the rate of appearance of E. And then the yield of D will be the rate of appearance of D over the rate of disappearance of A, and then the yield of E will be similar with the rate of appearance of E over the rate of disappearance of A. And polymath's a little bit sensitive in the fact that this RE, the rate of appearance of E, will actually be 0 initially, since the concentration of A will be 0 initially since we're only feeding in B. So we have to trick polymath a little bit to help it get past this first initial time point. It'll probably give you an error if you don't do this. So in one of the examples in your book, they say to, instead of having this explicit equation that's actually correct, having the rate of appearance of D over the rate of appearance of E plus a really, really tiny number, like 10 to the negative 10th. And so then that'll just essentially be a fudge factor to barely change the rate of appearance of E so it can plot it for you. And so then the last thing that we need to add is the final volume of our reactor, essentially the total volume of our membrane reactor that polymath needs to integrate to. So as we calculated this with the rate of diffusion of AN with the large R A factor, we can use the cross-sectional area times the length, which was the diameter of our reactor over 2 squared times pi times the length. So that's going to be, it was 6 centimeters, which I just converted to meters here, squared times pi, and then our reactor length was 20 meters, and then we can do the conversion factor of 1,000 liters per 1 cubic meter. And so then our total volume that we need to integrate to is 56.52 liters. So now we can plug all of this information in to polymath and solve. So this is the output graph that we got for the instantaneous selectivity of D to E, and as you can see there's a really sharp initial spike and then kind of drops off down to 0, and this is what we would expect for a membrane reactor. And so this is the output graph for the yield of D, and as you can see, it slowly decreases along the length of the reactor because the rate of disappearance of A is starting to increase as the concentration of D increases and the rate of the second undesired reaction becomes greater. And here's the plot of the yield of E down the length of the reactor, and then you can see it starts to increase as the concentration of D starts to increase down the length of the reactor, so the undesired reaction is starting to increase. But as I mentioned before, overall, this membrane reactor is going to give us a lot higher selectivity and a lot higher yield of our desired reactant, or desired product, than a PFR would.